This problem session is going to be based on a very special ring, the ring of quaternions. The ring of quaternions was discovered by Sir William Rowan Hamilton, an Irish mathematician, in the year 1843. So at the time of Hamilton, we already knew about the complex numbers. So this gave a way of multiplying pairs of real numbers. You could think of a real number as a pair a comma b, a pair of real numbers, as a complex number a plus b times I. And then using the rule I squared equals minus 1, you could multiply such pairs of real numbers. What Hamilton was trying to do is he was trying to find a way to multiply triples of real numbers. So he would try to write a triple of real numbers as a plus bi plus cj, and then try to see if he could find a rule for multiplying them that would result in a ring. And Hamilton was not able to do that. But one day he suddenly realized that if instead of triples you take quadruples of real numbers, then you can find a ring. So let's see how Hamilton did this. You're already familiar with the group of quaternions which we talked about in the first week of this course. So in order to have the group of quaternions, we had 4 matrices, 1 which is just the identity matrix 1 0 0 1, the matrix which I called I, which is the matrix 0 1 minus 1 0, the matrix J which I called 0 I 0, and the matrix K which is minus I 0 0 I. And we've seen that these matrices satisfy the relations I squared equals J squared equals K squared is the negative of the identity matrix, and that Ij is equal to K, but if you do J times I, then it's minus K, and then Jk is I, which is minus Kj, and Ki is J, which is minus Ik. So these were the rules for multiplying quaternions, and we had this group called the quaternion group, consisting of 8 elements, I, J, K, 1 and the negatives. Now the ring of quaternions is defined as H is the real span of 1 I J K. So what does this mean? These 4 elements can be thought of as vectors in the vector space M2C of 2 by 2 complex matrices. Now this is a 4-dimensional vector space over the complex numbers, and therefore an 8-dimensional vector space over the real numbers. And H is a 4-dimensional subspace of that 8-dimensional vector space spanned by these 4 obviously linearly independent vectors. Okay, so that's the definition of quaternions, and we endow it with 2 binary operations, addition and multiplication, both inherited from matrices. So H, then we endow it with plus and dot. This is matrix addition, and this is matrix multiplication. And that for you defines the quaternions. Okay, problem 1. Show that H plus dot is a ring. Okay, I already called it the ring of quaternions, but we need to check that it is really a ring. Okay, so we need to show certain things. We need to show that H comma plus is an abelian group, we need to show that H comma dot is a monoid. We need to prove associativity, and we need to prove unitality. So let's start with the first. So we want to show that H comma plus is an abelian group. So why is this true? Do we need to go and check associativity, identity, inverse, and so on? No, we don't need to. We just accept the fact to start with that M2C is a ring, and so M2C plus is an abelian group. So we just need to check that H plus is a subgroup. Indeed, 0 belongs to H. If P and Q are in H, then P plus Q is in H, and if P is in H, then minus P belongs to H, all because H is a linear subspace of M2C, the vector space M2C. So any subspace of a vector space is an abelian group under addition. Now the next thing we need to check is that H comma dot is a monoid. And again, we don't need to check associativity because it is inherited from M2C. That means we know that matrix multiplication is associative, so when we restrict it to H, it will also be associative. The only thing we need to check is that, well, firstly the identity, the unit of M2C is the identity matrix which belongs to H. So the unit is there, and then the only thing we need to check is that H is closed under multiplication. But this is not very difficult. If we have two elements, let's say P equals if P and Q are in H, then we need to show that PQ is in H. So suppose I write P equals S times 1 plus let's say V1 times I plus V2 times J plus V3 times K. The choice of this weird notation will become clear a little later. For now, it doesn't really matter, where S, V1, V2, V3 are in R, and Q is T times 1 plus W1 times I plus W2 times J plus W3 times K, where T, W1, W2, W3 are in R. Then we need to show that PQ belongs to H. So what we can see is that PQ, well, it's going to be S times 1 plus V1I plus V2J plus V3K, and we have to multiply that by T times 1 plus W1I plus W2J plus W3K. And this is going to be a sum of terms of the form So when you use distributivity to expand this product, is a sum of terms of the form alpha times xy, where alpha belongs to R, x, maybe I should write alpha into x dot y, where alpha belongs to R, it's just a scalar, and x and y are elements of the quaternion group Q. For example, one of the terms would be V1 times I into W2 times J. So that will be V1 W2 into I times J. And that's exactly what this alpha is V1 W2 and this x is I and y is J. But because Q is a group, XY belongs to Q. It's an element of Q itself. So PQ is a sum, is a linear combination of elements of Q. Hence, by definition of H, PQ belongs to H, because PQ is precisely the linear span of the elements of Q. For the associativity of multiplication, we don't need to do anything, because associativity is just inherited from M to C. It holds in M to C, and we're using the same addition and multiplication, so it must hold in H. And finally, the last axiom was the identity axiom, and that's also true because indeed 1 of M to C is 1, which belongs to H. So rather, not identity, I want to call this unitality, right? So we can conclude that H is indeed a unital ring, or what we just call a ring. Okay, the next problem, problem 2, is H commutative? Well, this is an easy one, right? What do you think? You're right, the answer is no, because Ij is k, but that's not equal to Ji, which is minus k. So the ring is not commutative. Is example of two things in this ring which don't commute. Okay, let's take a closer look at the multiplication. Earlier, while proving that H is a ring, I kind of chickened out of expanding this full product. I'll do that now, but I'll do it a little carefully so that it's things are somewhat manageable. And now you'll also see why I introduced that strange notation for writing quaternions. So here's the thing. So let's write V to be V1I plus V2J plus V3K for V1, V2, V3 in R cubed. So we're going to think of vectors in three-dimensional Euclidean space as quaternions whose this coefficient of 1 in a quaternion is called the real part. So and the rest of it, the coefficients of I, J and K added up, that's called the imaginary part, in analogy with the complex numbers. So we're going to think of vectors in R3 as imaginary quaternions of the form V1I plus V2J plus V3K, and that corresponds to vector V1, V2, V3 in R cubed. And let's write W equals W1I plus W2J plus W3K. And now the exercise is to write down the product of V and W. So I'll give it as a show that. So part A, show that if I multiply V and W, then this is equal to minus, so the formula is really beautiful. So this is multiplication in the quaternions, and now I'm going to introduce the dot product of vectors. So maybe from now on, when I'm multiplying quaternions, I'll leave out the dot entirely, as we often do in rings. V times W is minus V dot. So this is the dot product in R cubed plus V cross W. So what I mean by this is just a real number. So actually what I mean is that we're taking this times 1. Okay, but this 1 is going to be omitted in what I write from now on. And this is, well, just straightforward calculation. Just do it. So we have v1 times I plus v2 times j plus v3 times k multiplied by w1 times I plus w2 times j plus w3 times k. And so now let's look at the terms where we take the same term. I take the first term in the first factor and the first term in the second factor, first term in the second term in the first factor and second term in the second factor, third term in the first factor and third term in the second. So I dot I is minus 1, j dot j is minus 1, k dot k is minus 1. So I'll get exactly minus v1 w1 plus v2 w2 plus v3 w3. So you see this first part, v dot w showing up. And then what's the coefficient of I? So how many ways can I get I? I can get I as j times k. So I take j in the first factor and k in the second factor, or I can get I as the negative of k times j. So I'll get I times, and then I will take j times k. So v2 w3 minus v3 w2 plus j times, and similarly we'll get v3 w1 minus v1 w3 plus k times v1 w2 minus v2 w1, and that's exactly the right hand side. Okay, so before we go further, let me just recall for you what V cross W is. This is the cross product, right? And what is its geometrical interpretation? So V cross W. So it is a vector which lies in the plane in the line perpendicular to the plane spanned by V and W. And its direction is given by the right hand rule. So what is the right hand rule? So you look at my right hand here. So if my thumb is V, my index finger is W, then my middle finger is the direction in which V cross W will be. Okay, so that's what I mean by direction given by the right hand rule. So now the direction is completely determined. It's in the so once I know the plane spanned by V and W, then it has to be either this thing or it has to be thing in the opposite direction. But now I'm saying by the right hand rule that it will be in this direction, and the magnitude of this vector is magnitude of V times magnitude of W times sine theta, where theta is the angle between from V to W, so to speak. In the plane spanned by V and W. Okay, so that was the definition of cross products, just to remind you. Okay, let's move on. Part B of this problem. So suppose we know that S squared plus the magnitude of W squared, let's say V squared, I'll use the same notation as before, is not equal to 0, then show that so this P, remember, is the quaternion given by okay, and so let P be the quaternion given by S times identity, S times 1 plus V. show that P inverse is equal to S minus V divided by S squared plus norm V squared. And this is very easy. You just look at S plus V times S minus V, and then you multiply. We already know something about the product of two imaginary quaternions, so we'll use that. So this becomes S times V minus S times V, these cross terms. S commutes with V because the identity matrix commutes with everything. And then we have S squared, of course, and then we have the term V dot, V multiplied by V. But so this will be minus V cross minus V squared minus V cross V. But that's just sorry, it's plus V squared because over here we had a minus sign. There's a minus sign over here. So well, these terms cancel out, and V cross V is going to be 0 because the angle from V to itself is 0. So that sign term will kill it, and so what we get is that this is just S squared plus. So this is just a multiple of 1, and so when I say this, you can think of this as scalar multiple, and so from this the identity follows. Okay, so let's just pause to make this observation here, that every non-zero quaternion is invertible. This is very rare in a ring, and we know some examples of rings where every non-zero element is invertible, and those are fields like the real numbers, the complex numbers, the rational numbers, and then finite fields. But in fields, multiplication is commutative, and in the quaternions every non-zero element is invertible, but multiplication is not commutative. So these quaternions are an example of what is called a division ring. So quaternions form a division ring. Every non-zero element of H is invertible. This is what we call a division ring. A ring not necessarily commutative, where every non-zero element is invertible. We now come to the most interesting problem of this session, which is called the quaternion rotation identity. So I guess this is problem 4, the quaternion rotation identity. And how does it work? So suppose I take u to be in R cubed, a unit vector. So u1 squared plus u2 squared plus u3 squared is equal to 1. And I can think of this as an imaginary quaternion. So u is equal to u1i plus u2j plus u3k in the quaternions. And I will think of vector v in R3 again as a quaternion. V is v1i plus v2j plus v3k. Okay, so I'm going to think of vectors in R3 as imaginary quaternions, as I said before. And now let's take Q. I'll define it as cos of alpha by 2 times 1, of course, so this is the quaternion, plus u times sine of alpha by 2. So this is an element of H. Okay, so the problem is, show that the function V goes to Q, V, Q inverse. So Q is a non-zero quaternion because either cos of alpha by 2 or sine of alpha by 2 will be non-zero, and U is a unit vector. So in any case, Q will be a non-zero quaternion. We can definitely invert it. So what does this function do? Rotates the vector V about the axis U. So think of U as a vector in R3, think of it as an axis by angle alpha. This same alpha that's appearing in the definition of Q. In the direction given by the right hand screw rule. Or right-handed screw rule. So again, you look at my hand, the rule says that if my thumb is pointing in the direction U, then if alpha is a positive angle, then the rotation will be by angle alpha in the direction indicated by my fingers. Okay, so that's the problem. Okay, so let's see how we can solve this problem. So to start with, observe that both V goes to Q, V, Q inverse, and V goes to, okay, so let's just introduce some notation. Let's take R U alpha of V to denote the rotation of V by angle alpha about U, as given by the right hand screw rule, of course. RU alpha. That both these are both linear transformations. From R cubed to R cubed. But a linear transformation is completely determined by its value on any spanning set. So it suffices to show that, we want to show that these two linear transformations are equal, so it suffices to show that they are equal on some spanning set of R cubed. On a spanning set. So to start with, we will take case 1 where V is U itself, okay, the unit vector U. So in this case, of course, R U alpha of U, well, if you rotate U about the axis U, it doesn't change at all, so that's U itself. Okay, so we need to just calculate Q U Q inverse. So that's cos alpha by 2 plus U sine alpha by 2 times U times cos alpha by 2 minus U sine alpha by 2. This is from this last term is coming from the inversion formula, and then using distributivity we get cos alpha by 2 U times cos alpha by 2 plus U times U, but that's just uh, uh, so the real part will be the dot product of u with itself, but the negative, so that's minus 1 times sine alpha by 2. And now we need to take this and multiply it by cos alpha by 2 minus u times sine alpha by 2. So that multiplication formula for two imaginary quaternions makes life quite easy. And so now if you do this, then you'll get u times cos squared alpha by 2. That's the first term. And then you'll get u times u multiplied by cos alpha by 2 sine alpha by 2 with a negative sign. So that u times u gives just minus 1, so we'll get a plus sign now, and we'll get cos alpha by 2 sine alpha by 2. And now let's multiply this thing. So here we get again u times we get minus sine alpha by 2 cos alpha by 2, and then the last term is plus u sine squared alpha by 2. So these two terms cancel out, and these two add up to give u. So we see that the rotation and the QV inverse, they agree upon the vector u itself. Okay, and now let's take case 2 where v is perpendicular to u. If we can show that it's true for v equal to u and v perpendicular to u, then we've shown that these two linear transformations are equal for every vector in R3. So now we have Q inverse. Well, this is cos alpha by 2 plus u sine alpha by 2 v cos alpha by 2 minus u sine alpha by 2, and that's cos alpha by 2v. Let me write it as v cos alpha by 2, and u cross v sine alpha by 2 cos alpha by 2 minus u dot v, but u is perpendicular to v, so that term will go away. U dot v sine alpha by 2 cos alpha by 2. So let's not write that. So we've taken care of that, and now we have this multiplied by cos alpha by 2 minus u sine alpha by 2. But that's equal to, so now we have v cos squared alpha by 2, and then we have v cos alpha by 2 multiplied by u sine alpha by 2. So again, the dot product term, the real part will be 0, and we are only left with an imaginary part, which will be minus u cross v, minus v cross u, but I can write it as plus u cross v, and it will be accompanied by cos alpha by 2 sine alpha by 2. And now let's look at the second term in the first factor. That will first give me this was just u cross v, there's no cos alpha by 2, it is just u cross v sine alpha by 2. I'm sorry, right? There's no cos alpha by 2, I don't know why I put it. So I get U cross V whereas here I have U cross V cos alpha by 2 sin alpha by 2. Okay, that was the first term, and for the second term I have U cross V, again U cross V cos alpha by 2 sin alpha by 2, and then the last I take the second term from both factors and I get U cross V cross U. See, U cross V is already perpendicular to U, so it's perpendicular to U and to V, therefore it's perpendicular to U, and so the dot term will be 0 and I'll just get minus U cross V cross U sine squared alpha by 2. But this thing over here, U cross V cross U, is actually just V. So what you get is just V cos squared alpha by 2 minus sine squared alpha by 2 plus U cross V, and then we have 2 sine alpha by 2 cos alpha by 2, which is V times cos alpha plus U cross V times sine alpha. But that's just the formula for rotation about in the vectors V and U cross V, which means that it's a rotation by angle alpha in the axis perpendicular to U. And so that solves the last problem. Now this last property is actually very important in real life. I mean, well, so this quaternion rotation identity gives a very simple way to compute the rotation of vectors about any axis by any angle, and this is used all the time in computer graphics. So when you have your video game and you're running around and turning, every time you turn, well, you have an axis by which you turn and an angle by which you turn, and those computations before rendering are done using the quaternion rotation identity. So Hamilton's quaternions, discovered in 1843, well, they are still used today to give fast rendering of graphics, 3D graphics in video games. Now, isn't that cool?